All right, we're continuing on our discussion on atoms and continuing with spectroscopy, which deals with electrons going from ground state to excited state with the addition of energy, and then going from excited state back to ground state. And when they go from excited state back to ground state, they give off energy in the form of light. Okay, all right, first up, bell ringer. So you got to identify the number of electrons and neutrons in the following. So I'm going to kind of move on. I will ask you the questions in Edpuzzle. But for titanium, the electrons normally in an atom would be 22. All right, but because this has a +3 oxidation number, that means it's lost 3 electrons. All right, so that means that it's down to 19 electrons. All right, and then in terms of neutrons, it's the atomic mass, or the mass number, which in this case is 48 minus 22, which is 26. So it's got 19 electrons and 26 neutrons. All right, S minus 2. All right, its sulfur atom would have 16, but since it's a -2 charge, it gains 2 electrons, so it's going to have 18 electrons. All right, and then the number of neutrons are 32 minus 16, which is 16 neutrons. Okay, all right, so that's just a quick review of figuring out the neutrons and electrons, because those are the things that can change in a particular particle. All right, so spectroscopy. Normally we'd have a discussion about what you see here. All right, but what this is an image of the sky in a fairly dark area with a diffraction lens, which is a special lens that you can put on a camera and see. And what a diffraction lens does is that it slows down the light and it spreads out into its component colors. So you can see here that, you've got some, and this is stars. All right, you've got some stars that have, lots of blue, and then a little bit of the yellow in here, and a little bit of the red. You got some darker red, very little yellow, some more blues. They're generally not the same. All right, they're similar. They can be similar. And this allows us to figure out what elements stars are made up of, or what elements that they are burning or combusting out there. All right, we do this on a much simpler scale by using diffraction lenses in lab. Unfortunately, we can't do this year, so I'm trying to figure out something to do virtually. All right, but it's kind of a cool thing. Some place that you can see something like this, or you can get the glasses. They're called diffraction glasses, which they're not very expensive. They're like $1. They're like, you would call them 3D glasses, but they're not 3D glasses. They have a different lens in them, but they're that type of glass, the plastic or the paper without the lens in them. Last I knew, Lowe's and maybe Spencer's sold Christmas light glasses. All right, and those are basically diffraction lenses. So what it's going to do when you look at Christmas lights, it's going to spread it out into its component color, so it looks a lot different than it does just with your eyes. Okay, so that's the basis of spectroscopy, is we're looking at these things with a special lens. All right, we're going to see what's called bright line spectrums, and this is kind of an exaggeration of it. All right, but you take some form of light and you're going to pass it through a lens. This prism is acting at the lens, or representing the lens, and then it's going to split it out into its component bright lines. These bright lines are representing electrons that are going to go from the excited state back to the ground state for a given sample. All right, we're going to talk about, for the most part, individual elements, very few compounds we're going to get into discussion about. All right, but what this shows is when you look through this special lens, you're going to see a bunch of bright lines. When you look through it with just your eyes, your brain's going to process as one color. All right, that's the difference between when we did the flame test thing and when we do bright line spectrums or spectroscopy. All right, the way our eyes see things and the way other lenses see things. All right, but ultimately, the energy that's emitted is a term that gets people freaked out all the time. Emitted means given off. All right, we use these bright line spectrums for elements to kind of identify them. It's their own signature or fingerprint. All right, so if you look here in the background, you can kind of see the rainbow: red, orange, yellow, green, blue, indigo, violet. If indigo is a color, I don't know, I'm not discussing that. But then you got to ask yourself, how many bright lines do you see? All right, and this is the challenge that comes into play when we do this in class, is you got to discern between what's a bright line and not a bright line. All right, obviously this reddish one is definitely a bright line. This yellow one's definitely a bright line. All right, is this first blue one a bright line? This next one is, or I guess you wouldn't call that blue, light blue or something like that. Is this line a bright line? Are these two in here in the green area bright lines? Are these two darker blue ones a bright lines? Are these really dark, is this really dark blue a bright line? Definitely. So I would definitely say it's got 1, 2, 3, 4, 5, 6. We can argue about these two right here and those two right there. All right, and this is where the qualitative part of it comes into play, or subjective part of it. All right, if we have instrumentation to actually measure this, we can measure the wavelengths of light. All right, but this is representing, these bright lines are representing, let's say there's six different electrons that are being excited, and then they're falling back to ground state. All right, and they fall back to ground state in these repeatable patterns for a given element. All right, and we can use it as quote unquote fingerprint to identify these elements. So there's types of spectra. There's continuous, there's bright line, and then bright lines, you can have what's called an emission spectrum and an absorption spectrum. They're just the opposites of each other. So a continuous spectrum is like a rainbow. All right, that's why I put a rainbow up here. You kind of, where one color ends and one color begins, you really can't tell. They kind of blend together. The emission spectrum is what's given off, the energy given off. All right, and an absorption spectrum is just the energy being absorbed. So you can see that they're contrasts of each other. These both represent hydrogen. All right, one's showing an emission spectrum, one's showing an absorption spectrum. That's really as far as we go to this. And in our level of chemistry, when you get to college, you'll talk about different instrumentation that can measure absorption or emission. We just don't have that equipment here in high school. All right, but in our lab, at our level, a continuous spectrum is produced by the heating of a solid material. All right, we would do this by using an old school light bulb. All right, an incandescent light bulb. And the way an old school light bulb works is it's got a little piece of tungsten in there that glows when electricity is passing through it. So that's actually using a solid piece of material. All right, and we can see that continuous spectrum. So you can see in this image down here, you've got a light bulb. If we just watch it with our glasses, you'll see whatever the light is that it gives off. If we put it through those lenses or the diffraction lenses, that's what this thing here represents. If you put it through there, then you would see a continuous spectrum. You'd see these rainbows all over the place. Kind of give you a headache if you do it a lot. If we heat up a gas, you're going to get an emission spectrum, and that's kind of what we do in lab with spectroscopy, and that's what we're going to kind of do. If you use a cold gas, if you cool it down, it's going to produce an absorption spectrum, but we don't really differentiate between the two. We're just going to call it bright line spectrums. All right, so when it's emitted by a gas, so the difference between the continuous spectrum and the bright line spectrum is this is a solid material being heated, and then the bright line spectrums are from a gas being heated or excited. All right, so you get the bright line spectrum. So here you'll see a bunch of bright line spectrums for different elements. You can see that, hydrogen's got simple, 2, maybe 4 lines, depending on who you're talking to. All right, down to neon, which has got an incredible number of lines in here. All right. And we used to, in the lab, if we were in class, we would actually draw these out and see them, and you can actually measure the distance between them and calculate all kinds of energies. All right, but we're going to simplify it greatly for this year. Okay, so you can see these bright lines. Now notice some people will always ask, well, how does hydrogen have 2 bright lines if it only has 1 electron? That still can happen. The electron can absorb energy and bump up once and then come back down, and then absorb a different amount of energy and bump up and come back down. All right, but hydrogen's always going to have these repeatable 2 lines, and there's usually a 3rd and a 4th line as well. But it's unique to just hydrogen, and you'll look through here, and literally what we do is we just compare vertically which lines are there and which lines are not. So like if you had a compound with hydrogen and let's say oxygen right here, all right, which is water, all right, you would have a combination of all these bright lines. All right, so it's kind of a cool thing to see. So, and there's all kinds of equipment that will do this, and we do it on a very subjective level here in high school. So like I just said, a combination of elements or a compound would create a combination of spectral lines. So we'll simplify down the diagram right here. So here we have element X, it's got this purple bright line, the orange and the red bright line. Element Y, it's got the yellow, the teal, I don't know what color you call that, and another kind of orangey red line. If you were to have a mixture of these 2 things or a compound of these 2 things, all right, their combined spectrum, all right, would look something like this. Now, what people get confused on is, do you need to see 2 different, if we're going to call these red lines? No, if they're in the same energy wavelength, then it's going to appear as 1 line. All right, but to find out what elements are in this compound, you have to have all of the lines. So here, element Y has the green or turquoise line, it has the yellow line, it has the red line. So Y could be in there. It doesn't mean it is, it could be in there. And then element X would have to, if it's in there, it would have to have the purple, and then the orange, and then that reddish colored one. All right, so the mixture or the compound of the elements is actually a combination of the individual ones. Okay, so remember, each elements give their own unique pattern. So that's why I said before, it's kind of like a fingerprint. All right, and it's unique to that element. This is a very one where we black out the background noise, so to speak, and you can see the 4 individual bright lines, and then you can see a number associated with this, and this has to do with the wavelengths. Longer wavelengths have less energy, shorter wavelengths have more energy, people who've taken physics. All right, and we can actually measure those, but we're not going to measure them in here. All right, and there's chemical analysis to do this for us, or there's instrumentation that will do it as well. All right, how you've seen this maybe is something called a neon sign. All right, this thing down here is a neon sign. All right, I chose this one because it's got 2 different colors in it, because technically a neon sign only has this orangey red color. All right, if you have any other color is going to be some other element. People will generically call them neon signs, but they're not really neon signs. The only true neon sign is the one that's this kind of orangey red one. If you see it on pizza shops, sometimes they'll say hot pizza, or maybe it's an open sign. It'll say that it's open. All right, so this is a spectral tube. It's basically just a tube with neon gas in it. And it's got 2 pieces of metal inside on the opposite end, so you can pass electricity through it. And when it excites it, when you turn on the electricity or you plug it in, it will excite the electrons, and it'll produce this color with our eyes. This left thing here is the color we see with our eyes. If we were to put a lens on or to put the glasses on, we would see all of these bright lines in here. All right, and this bright line spectrum is very unique to helium, or to neon, All right, to neon. Okay, and you'd have to go through and count them, and you could actually measure the thickness of them and things like that, but we're just kind of talking about it for today. So here we go. So knowing what you know, all right, I'm going to ask you now to answer this question. You have an unknown element up here, and I'm going to tell you that it's one of these elements down here. And all you have to do is match up and figure out which one it is. So remember that for it to be the element, it's got to have all the lines. So you can kind of narrow some out pretty quickly. If you look here, magnesium, it can't be magnesium. It doesn't have that color line right here. I'm not going to say a color name because people see colors differently. All right, it's definitely not hydrogen. It could have hydrogen in it, maybe. It's got a red line here, but it doesn't look the same, and it doesn't really have the same kind of intensity blue line. So hydrogen's not in there. All right, sodium, all right, definitely doesn't have this thick blue line, so we can rule out sodium. Calcium, if we look, it's got the 3 lines there. It's got that kind of green pattern here. It's got the thick green and the reds up here. So it's definitely got calcium in it. Does it have iron in it? I don't think so. It doesn't have all these lines. I know I'm trying to get off the bottom of the screen so that exit sign will disappear. All right, it definitely doesn't have the iron in there because it doesn't have all the lines of iron. So that's just kind of our quick little end wrap up question for here. And this we'll just leave with this image right here.